So, hi everyone, welcome to today's SIML webinar. Our speaker will be Jianke Yang, and session chair will be Bharat Ramsundar. I'll go ahead and introduce the session chair. So, Bharat Ramsundar received his BA and BS from the UC Berkeley in Electrical Engineering and Computer Science and Mathematics, and was valedictorian of his graduating class in mathematics. He did his PhD in computer science at Stanford University, where he studied the application of deep learning to drug discovery. Bharat's graduate education was supported by the Hertz Fellowship, which is a very selective graduate fellowship in the sciences. And he's currently the founder and CEO of Deep Forest Sciences, a startup building a no-code platform to allow biologists and chemists to leverage scientific foundation models. Bharat is the lead author of TensorFlow for Deep Learning, From Linear Regression to Reinforcement Learning, which is a developer's introduction to modern machine learning with O'Reilly Media. And he's also lead author of Deep Learning for the Life Sciences. Thank you, Bharat, for joining and being our session chair. I'll hand it over to you.
All right, it's a pleasure. I'm really, thank you for the kind introduction, Keith. I'm really looking forward to today's talk. Jianke Yang is a second-year PhD student in computer science at UC San Diego. His advisor is Professor Rose Yu, and his research interests include physics for machine learning and geometric deep learning. Today, he's going to present to us his work on generative adversarial symmetry discovery, which is an example of machine learning methods for scientific discovery. I think in general, like symmetry discovery is something I've been, excited to learn more about for a while. So I'm really looking forward to your talk, Jianke.
Thank you, Bharat, for the introduction, and also thank you, Kate, for the introduction, for the invitation to this event. I'm really glad to talk here. And today I'm going to present our works on generative adversarial symmetry discovery. So this talk will consist of two works. One of them we have published earlier this year at ICML conference, and the other is our recent follow-up work. So let's start with a bit of the big picture of physics-guided machine learning so we can place this work in a better context. So when we apply machine learning methods to physics-related tasks, such as predicting the real-world fluid dynamics, particle movements, or molecular properties, a purely data-driven approach may not be able to produce fully physically correct or scientifically valid results. For example, the fitted function from a neural network may not obey the governing differential equation of the system, or may not respect the conservation laws for some quantity. And therefore, in physics-guided deep learning, we explicitly encode these first principles from physics into the machine learning models in order to provide some useful inductive biases and also improve generalization ability and sample efficiency so that we can finally build trust in AI for these scientific tasks. And our work focuses on one of these points, which is symmetries in neural networks. The symmetry can refer to many things in different contexts, and it's good to clarify what kind of symmetry we are interested in our work. By symmetry, we are referring to the invariance or equivariance property of a function. And to be more specific, we need to introduce the mathematical concept of a group. Group is a set with a binary operation defined on its elements, which satisfies the group's axioms. So we can take two elements of a group and get another by this operation. And this operation needs to be associative, and the group must have an identity element. And also for each group element, we must have an inverse, which can get back to the identity. So we often use group to describe a set of transformations on the input. For example, all the planar transformations form a group SO2, where the operation is simply the composition of two transformations. And then for a given group G and the function f, we say that f is G invariant if or an invariant to G transformations if the function output stays the same, no matter how the input x is transformed by the elements in G. Or in mathematical terms, f of gx equals to f of x. A typical example of this is image classification, where the input is the image and the output is the class label. Generally speaking, if we rotate the input image by some angle, the output label should still stay the same. Then similarly, the function can also have equivariance property, which means that the output will transform in the same way by the same group element as the input, or in math terms, f of gx equals g of fx. For example, consider this task on the right of predicting the future dynamics of several of a spatial field. And if we rotate the whole coordinate system, then the input and output feature vectors will rotate by the same amount. And since invariance here is actually a special case of equivariance, I will just use the term of equivariance in the following discussion. Equivariance has become a very important inductive bias in neural networks. And in fact, it has become a very, very popular topic recently. So if you search the literature with keyword equivariance or equivariant neural networks, you're likely to find the number of related papers growing exponentially. For example, as an extension to the original convolutional neural networks, which exploit the translational symmetry in 2D plane, there have been general E2 equivariant CNNs, which is equivariant to all Euclidean transformations, including translation, rotation, and reflection, and also spherical CNNs, which deal with signals on spheres and respects the SO3 rotation symmetry in 3D. Also, as is shown in this figure, graph neural networks can also be extended to have equivariance to this kind of Euclidean transformations. So if the positions of the graph nodes are all transformed like by a rotation, then the feature vectors are, which is the orange arrows here, are transforming the same way. However, most of these existing equivariant models require knowing the symmetry a priori before constructing the model. For the equivariant GAN we just mentioned, if we do not know the Euclidean symmetry exists in this data set and instead there is some like unknown symmetry, then this Euclidean equivariant model cannot be readily applied. And also, there has been research, in fact, research of our group, indicating that enforcing a strict symmetry can be harmful to prediction in real-world data. So as this figure on the right shows, if the data is not perfectly symmetric and we enforce strict theoretical symmetry in the model, the performance may even decrease. So generally speaking, incorporating the a priori knowledge of symmetry is often unrealistic and also suboptimal in practice. To address this problem, we aim to develop a method for deep learning models to automatically discover symmetry from data. In this way, the model does not need human knowledge input about the symmetry and can play the role like an AI scientist itself. And it can not only make predictions, but also reveal the underlying symmetry mechanisms of a task, which can then relate to other useful physics properties, such as conservation laws and others. And this is an overview of the framework we proposed. It follows the design of the generative adversarial network, and also we are using the theory of Lie group and Lie algebra to model continuous transformations, which I will talk in more detail later. And putting all these together, we call it LieGAN. And I will get into the details of this method in a little bit. And before that, I will briefly introduce some other existing models in symmetry discovery and compare them with our framework. So first, there is this framework called meta-learning symmetries by reparametrization. Its claim is that symmetries can be characterized by the pattern of weight sharing in neural networks. For example, the kernel weights in convolutional neural networks are shared across all the locations, and it has translational symmetry. Therefore, this work proposes to decompose the weight into two parts. One deciding the weight sharing pattern, which is the symmetry matrix here, and the other representing the actual weights. But the problem with this approach is that the model size scales linearly with the group size, which is suggested by this proposition. And this means that it can only be applied to discrete transformation groups, but not continuous groups with infinite number of elements. And another interesting work is called Algerino. It also aims to find invariance and equivariance in data. However, their setting is slightly different because they are trying to find the extent of symmetry within a given group. For example, we know that image classification has rotation symmetry, but can we rotate the images by arbitrarily large angles and expect the output to be the same? At least for the digit classification, we know that the answer is no, because rotation up to 90 degrees will cause confusion between the digits 6 and 9. So Algorithm tries to find the extent of a known symmetry like this, but it cannot be applied to discovering previously unknown groups. So compared to these methods, our framework of LieGAN deals with various types of symmetries, including continuous group, discrete groups, and subset of either given or unknown group. And next, I will introduce the details of our methodology. First, we need to define the problem, right? So we are trying to find the unknown equivariance property of a given data set associated with an input space X and an output space Y and an unobserved function mapping inputs from to outputs. So we suppose a group G acts on the input and output space X and Y via its two representations. So the group representations here basically map each group element in G to some linear transformations of a given dimension, and the N and M here denote the input and output dimensions. And GLN, which is the general linear group, includes all the linear transformations of a given dimension. So while the group itself is an abstract mathematical object, what really matters here is how the group elements transform the data through its representations. And the symmetry we are trying to discover is these group representations that satisfy this equivariance formula, which is gy equals f of gx. And yeah, so here comes a key motivation for our method. We observe a connection between the previously defined symmetry or equivariance and the data distribution. Basically, if we have an original distribution P sub D, and each data sample from this distribution is transformed by some element in the symmetry group, in this case, it is SE2, which consists of all the rotations and translations. And then these samples are transformed by these group elements to form a new distribution P of T. Then the two distributions PD and PT should stay close to each other. And this example of image classification, if we randomly sample some Euclidean transformations such as rotation and translation and apply them on images, and we will see that the transformed data set should look similar to the original one on the distribution level. And this is a result of this SE2 symmetry. So this connection naturally leads us to the idea of using a generative adversarial network to detect symmetry. So let's recall the setting from the original GAN, where people use a generator to generate fake images and form a generated distribution. And they use another discriminator network to learn the difference between the true and fake distributions. For our purpose, we can use the same idea, but because we are trying to learn some transformations that preserve the distribution instead of how to generate realistic images from scratch, we have a key difference in the design of our generator. So instead of random noise, the generator takes in an original data point, X and Y, and then all right. So the generator takes in an original data point and samples a group element according to some distribution defined on the general linear group, which is the entire search space of symmetry, including all invertible linear transformations. And then it transforms data using this G sample. The other part, including the discriminator and the loss function, are the same with the original GAN setting. So intuitively, if the generator can generate symmetry transformation, then its output will still be a valid data point. Or we can say that the generator output has a distribution that is similar to the original data distribution. For example, this figure shows a task of predicting future three-body movements, which has rotational symmetry. because if we rotate the entire system by the generator, the rotated input-output pair in this Gx and Gy will still make sense. And therefore, through this kind of generative adversarial training, the generator fools the discriminator by learning the correct set of symmetry transformations and making it really hard for the discriminator to distinguish the original and generated samples. And this fulfills our purpose of symmetry discovery. Oh yeah, and this is just a zoom-in view of our design of the GAN generator. So basically, what we do is that we sample group elements from a distribution mu parameterized by beta, which is defined on the symmetry group, and we transform the data points x and y using the group representations of this element. And then the loss function, it is you can notice that it is roughly the same as the original GAN setting, except that in the fake generator loss part, we are using the generated sample from original sample instead of from random noises. And under this framework, we prove that this training procedure can indeed discover symmetry if the dataset obeys some reasonable assumptions. And the general idea here is that in theorem 1, when we have very ideal conditions, the generator loss can achieve global minimum, which is 0 JS divergence, by learning the largest possible symmetry group. And in theorem 2, when we have less ideal but still practical assumptions, we prove that learning the subset of correct symmetries will lead to a lower loss for the generator than learning a completely wrong symmetry. So due to time limit, I will not get into all the math details here, just to ensure that this reasoning from generative adversarial training to symmetry discovery is not just an intuition, but also theoretically grounded. Okay, so one of our goals is to expand the search space of symmetries to continuous transformations. And this search space has not been addressed by previous work so far. And for continuous transformations, we can represent them by Lie groups and Lie algebras. And in our model, we use the generator to model a distribution over continuous Lie groups. And this involves a little math, but the key message here is that we can describe any connected Lie group, which is both a group and a manifold, by a corresponding element in its tangent vector space at the identity. And we call that vector space the Lie algebra. And then we can use an exponential map from this vector space to the Lie group to map any vector space element to the group element. So that means that we can use a basis to describe this vector space, Lie algebra, just as any other normal vector space. And to parameterize a distribution on this vector space, we only need to have a distribution of the linear combination coefficients for the basis vectors. And here the coefficients are the W, and the basis vectors are denoted in LIs. And then we combine them together to get any vector space elements. And putting it all together, we sample from a distribution of W's, and then W's are the coefficients for the linear combination, and map it to a group element using this exponential map that acts on data. In practice, we choose a multivariate Gaussian for this distribution gamma. And when training, the generator updates the LIs here, which is the basis for Lie algebra, and this decides what kind of symmetry transformations it is producing. And on the other hand, the distribution over coefficients, this gamma, can either be fixed or updated depending on the purpose of our discovery. For example, if we want to find only a subset of a group where the function is equivariant, recall the image classification 6 and 9 example, we can simultaneously learn the Lie algebra basis LIs and also learn the variance of the Gaussian distribution. So this parameterization allows some flexibility in our framework, making it possible to discover continuous symmetries, discrete symmetries, or even symmetries of subsets of groups. Yeah. And yeah, we also developed the pipelines for using the discovered symmetry in prediction tasks. So our model explicitly represents symmetry in the form of Lie algebra basis Li, which can be plugged into many existing equivariant network designs to create new equivariance with respect to the group that our model discovers. And I will talk about one example here, which is the equivariant graph neural networks, equivariant GNN. Compared to vanilla graph neural network, equivariant GNN uses group invariant feature for message passing. For example, on the right is the formula for the Euclidean group equivariant GNN. We know that Euclidean transformations preserve Euclidean distance between the nodes, and therefore this network uses this distance, distance in the highlighted to compute the edge messages, which makes the entire network equivariant to all Euclidean transformations, including translation, rotation, and reflection. However, the use of this Euclidean distance is restricted to the specific group of Euclidean transformations, and we wanted to extend to arbitrarily groups discovered by our LieGAN. So we develop a procedure to calculate a group invariant metric tensor, which makes the distance invariant to the given group transformations instead of fixing it to the Euclidean transformations. Specifically in this equation for message passing, we use a metric tensor J to compute the inner product as the quadratic form U transpose JV, and also the norm similarity. And we show that for a given Lie algebra basis, we can derive a metric tensor that is invariant to the corresponding group transformations by solving this equation, L transpose J plus JL equals 0, where LIs are the basis vectors we discover. And in practice, because the discovered LIs can have some numerical error, this may not have a perfect solution, and we use some optimization techniques to solve for an approximate J. And we also add a small regularization term here at the end to avoid zero solution. And in this way, we can construct a graph neural network that is equivariant to an arbitrary discovered Lie group. And we will show the performance of this modified GNN in the following experiments. Okay, now finally, we can look at some example symmetries that LieGAN discovers from data. And let's start from an easy one, the two-body trajectory. Here, our task is to predict the future dynamics given the past observations, and the input and output are the planar positions and momenta of two moving masses. And by concatenating them together, we can have an eight-dimensional input and output. And the main result here is in the plot B, where we set the LieGAN generator to have only non-zero entries in the 2x2 diagonal blocks in order to prevent the combination of position and momentum or the properties of different particles. And LieGAN can indeed discover the correct rotation symmetry in this case, very close to the truth in plot A. Besides that, we also use a different parameterization for LieGAN in plot C, where we allow more non-zero entries. We allow the interactions between the positions of the two objects and also between their momenta. Although this one looks very different from plot A and B, we also prove that this is just another representation of the same rotation symmetry in this setting. And yeah, after discovering this kind of symmetry, we use it in the prediction task by either equivariant model, which is the EMLP, equivariant MLP here, or data augmentation. We can see that the symmetry from LieGAN in the first row leads to the second best test performance. It is just slightly behind the ground truth rotation symmetry, and it's better than the other discovered symmetries from other discovery methods. Okay, next, we also show that LieGAN can discover symmetry groups with more complicated structure. So here we consider a task of top-quark tagging. It's basically some particle physics data set. And the task is basically the binary classification between the top-quark jets and the background signals. And the inputs are the four momenta of the particle jets, and the output are the class label. we know that the four momenta are invariant to Lorentz transformations, including the normal 3D rotations and the boost along three spatial dimensions. And they can be described with the six-dimensional Lorentz group denoted as 013 here. And in our experiment, we set the dimension of the Lie group to 7, which is slightly more than enough, slightly more than the ground truth. And we can see that, the 7 basis vectors of the Lie algebra here. The third, sixth, and seventh corresponds to the 3D rotations, and the first, second, and fourth channel correspond to the boosts along different spatial dimensions. And on the very right is the computed invariant metric of this discovered symmetry, which we mentioned earlier. This is used to construct the equivariant GNN as we, as a modification of the original Euclidean equivariant GNNs. And before jumping to the prediction task, we first visualize the original data distribution and the transform distribution with the discovered symmetry to verify that the discovered symmetry is indeed valid. And we can see that the highlighted portion of samples are transported to new locations. For example, in this first marginal distribution of E and P of X, it is in the top left corner, and in the right is the transform distribution. It is slightly shifted downward. But although these individual samples are shifted to the new positions, the overall data distribution remains similar. And this is exactly the effect we want to see for a valid symmetry. It is non-trivial and it preserves the data distribution.
So, Jianke, I think we might have a question from Keith.
Yeah. If you go back, I think one slide. So I'm trying to understand what the matrices are representing here when you construct the metric on the right there. So what do the indices of these matrices correspond to?
Okay, so in this task, we are trying to discover a multidimensional Lie group, or by discovering a multidimensional Lie algebra. So we have a 7-dimensional vector space as the Lie algebra. And of course, that 7 is a hyperparameter that we're using for our method. So here, the 7 matrices on the left correspond to the basis vectors of that 7-dimensional vector space. And basically, each matrix corresponds to a different kind of transformations that our generator can generate. For example, in the third one, we can observe a skew symmetric matrix. And if we take the matrix exponential of this Lie algebra generator, we can have the regular 2D rotation matrix like cosine theta, negative sine theta, cosine theta. So this corresponds to rotation in 3D space around a particular axis. And for other, like in the 6th and 7th channel, there are both skew symmetric matrix, which indicates the rotation symmetry along like 2 other axes.
Yes, so I guess, are these matrices learned, or
yeah, so these are exactly what we are learning in the LieGAN. So this is the Lie algebra basis that we mentioned earlier. And by learning this kind of matrices, we are actually letting the model learn what kind of symmetry transformations, whether it is rotation indicated by the 3rd, 6th, or 7th channel, or it is the scaling or boost, we call it in the context of Lorentz transformation, indicated by the 1st, 2nd, or 4th channel, or whether it is some other kind of transformation, such as translation and other things. So these are the learned components of our method.
Okay, thanks.
Yeah, and for the matrix on the right side, it is the invariant metric that we compute according to the previously mentioned procedure for equivariant GNN. So basically, we want to compute a metric tensor to make the GNN equivariant to the discovered symmetry instead of some prefixed symmetry. Yeah. Okay, thank you for the question. And Yeah. So for the prediction in this task, we use the equivariant GNN constructed by the invariant matrix referred to. So we refer to the equivariant GNN as the LieGAN in this table. So we can see that the LieGAN almost reaches the performance of Lorentz net, which explicitly encodes the correct Lorentz symmetry and outperforms the models with no symmetry or wrong symmetry, which is the equivariant GNN with respect to Euclidean transformations here. And yeah, we also include some synthetic dataset examples to show that our model can discover discrete symmetries. For example, here we explicitly define the function f of xyz like this. Because of this modular, it is kind of have a discrete symmetry with respect to rotations up to 2 pi divided by k. And here we can see that the highlighted portion of the data sample is transformed to a new section with our discovered symmetry, and while the overall data distribution stays similar. So this is an example of our model discovering the discrete symmetries. And also we include another example to indicate that our method can even discover symmetry groups on the complex number field. So here we can see that the symmetry of this defined function is special unitary group. And when applied to this complex case, our method can still discover a Lie algebra basis that is equivalent to the standard basis for SU2 upon a change of basis. And yeah, to sum up for LieGAN, LieGAN discovers the symmetries of general linear groups from data, and it produces an interpretable Lie algebra basis as the discovery result and has larger search space than previous works. And we also have the pipelines for using the discovered symmetries to some downstream prediction tasks. However, so far our method still has some limitations. So we mentioned that it can discover any linear symmetry transformations in the general linear group. Although it discovers really a lot of common transformations such as rotations, translations, and scaling, it's still only a small portion of all the possible group actions. And we can only successfully discover the symmetries when the observations are measured in an ideal coordinate system. So in our recent follow-up work, we extend LieGAN to a new framework to discover the symmetries of nonlinear group actions on data. So it is called the latent LieGAN, and we abbreviate it as the LieGAN. So we apply this framework to some data sets of high-dimensional and nonlinear dynamics and saw it work effectively. And this framework builds on the top of LieGAN, so I will just introduce some additional components and then present some experimental results. Basically, we want to model the nonlinear group transformations on data. Again, the group action or the group transformation is a function that takes a group element and another object from the input space V as input and outputs a transformed object. So it specifies how the group transforms the data. And when this function is linear with respect to the data space V, it becomes a group representation and can be learned by the original LieGAN. But when it is nonlinear, we need to introduce this new method. And in our new framework, we propose to decompose the nonlinear group action into two functions parameterized by neural networks, which is phi and psi here, and a group representation pi of g. We can verify that if phi and psi here are inverse of each other, then the pi prime defined in this way is indeed a group action that is compatible with the group element composition. And this gives us the intuition that phi and psi, because they are inverse of each other, they form an autoencoder that maps between the input vector space and a latent space. So through this kind of decomposition, our method learns both the symmetry group acting on a latent space with its linear representation pi of g, and a pair of inverse mappings between the input space and the symmetric latent space. And in practice, we train these two networks phi and psi under a reconstruction loss. And the final loss consists of both the reconstruction term and the original GAN term. So one thing about this framework is that it allows really a lot of freedom in the model, because you can imagine there are infinite ways of mapping the observations to latent representations without losing information. And different latent spaces may or may not have linear symmetries. We observed two failure modes with undesirable latent space structures. So first, the latent embeddings can collapse to a low-dimensional subspace under the symmetry discovery objective. For example, this happens in figure A here, where the two dimensions of the latent representations have almost the same values. And in this case, a non-trivial group representation on this latent space will actually act as identity. So imagine you have Z1 equals to Z2, and a linear transformation represented by a 2x2 matrix, where the sum of each matrix row equals 1. Then you actually have an identity transformation on these Z1 equals to Z2 latent vectors. But because of the dependency between the latent dimensions, this transformation can be represented by non-trivial matrix group elements, such as a non-trivial matrix with sum of each row equals to 1. So we call this phenomenon a fallacious symmetry, and it can provide an easy workaround for the symmetry generator, because there are indeed a lot of solutions that correspond to the identity transformation, which can, of course, preserve the data distribution because it is not changing anything. Of course, we don't want this kind of thing to happen. So to prevent this from happening, we use the orthogonal parameterization in the final output layer of the encoder to enforce different output in different dimensions. And also another failure mode occurs in the figure B here, where the latent representations are not centered at the origin. So this is not desirable because the linear group representation or the matrix multiplication implies that the vector space is centered at the origin. And if this is not the case, if the coordinate system is biased, such as in figure B, where the latent representations throw on a circle centered at 1, 1, we can see that even the true SO2 rotation symmetry cannot preserve the distribution. So therefore, we enforce the latent space to be unbiased by normalizing each data batch to have zero mean before applying the symmetry generator transformations. Okay, so these are actually some technical details, and now we can move on to see some cases where this new framework becomes effective. Oh, questions?
Yeah, a quick question about the case B there. So does this imply that you can only ever capture global symmetries?
Yeah, that's true. Because if you look at our generator, you will find that it only takes it does not take the access input, which means that the symmetry is global. It is acting on the entire domain in the same way. So indeed, it cannot discover local symmetry. We're actually planning to do this for future work, where we try to incorporate the local symmetries by also taking the X as input as a generator, so they can output different transformations on different regions of the domain. So yeah, that's a good question. And for this figure B, I think it is suggesting more than of course, it is suggesting it cannot discover local symmetry, but it is suggesting more than that because we need our latent space to be centered at origin, and it can also not model the translations. So to model the translations, we might need to add another dummy dimension to the latent space, like add a 1 as the final dimension, and use the linear combination of the original dimensions and this dummy dimension of 1 to produce the translations. So indeed, this provides some insights of how to improve our method further. Yeah.
Hmm.
Okay, so yeah, thank you for the question. And as the first example for this renewed framework, we consider a high-dimensional observation of a reaction diffusion system. And this system is governed by some partial differential equation, and we simulate the system within a rectangular domain for some time steps. And then we discretize the 2D space into a 100 by 100 grid. So we have an input dimension of 10,000. And in this case, it is very difficult, if not impossible, to find the linear symmetry transformations of the high dimensional observations, because that will essentially lead to a 10,000 by 10,000 matrix representation. Instead, we can discover the linear symmetry in a relatively low dimensional latent space. And here we set the latent dimension to 2, and we can discover an approximate rotation symmetry, which is shown in figure A. So we can observe this nearly perfect circular shape. And if we apply this symmetry, nonlinear symmetry, to the data samples, we can see that the transformed samples in figure C actually look very similar to the original samples in the figure B. While we also applied the original LieGAN with the linear transformations, and we can see that in figure D, they introduce some very obvious artifacts. And apart from this example, we also observed that the absence of linear symmetry is not exclusive to this kind of high dimension observations. And we also consider 2 examples of very simple nonlinear ordinary differential equations, which are the nonlinear pendulum here, and also the so-called Lotka-Volterra equations. So they are a pair of equations that describe a predator-prey interaction and how their populations depend on each other. And the pendulum trajectory is shown in the first row, where the 2 dimensions correspond to the angular displacement and momentum. And the predator-prey system of this Lotka-Volterra equations is shown in the second row, where the 2 dimensions are the population density of 2 species. So in these 2 examples, there are no linear symmetries in the original up to the observations as you observe in the figure A. But if we map them to some 2D latent representations in figure B, we can see some elegant circular or elliptical trajectories, and of course the rotation symmetries, perhaps up to a certain scaling in different latent dimensions. Yeah, and then we also study the effect of latent dimensionality, which is, as mentioned earlier, a hyperparameter for our method. Because in practice, especially for high dimensional systems, it is very hard to choose the perfect latent dimension that matches the intrinsic dimension of the system. So that we want to see if this method ours can still work well in a less ideal setting. And therefore, we consider the reaction diffusion system again and use a 3D latent space instead of 2D. And the result here is that we discover a rotation symmetry around a particular axis indicated by this skew symmetric L. And the latent representations roughly dwell on a 2D circular subspace in this left figure. And on the other hand, if we learn a latent space without encouraging any symmetry, we will have a much more complicated latent structure on the right. And after discovering all these latent symmetries, I want to talk about a really exciting application of it, which is joint discovery of the governing equations. So typically in these dynamical systems, such as the reaction diffusion system and nonlinear ODEs, we want to find a symbolic and often parsimonious governing equation that describes the dynamics in an interpretable mathematical form. And we often do this in a latent space for a high dimensional system, because if we directly express the equation in, say, 10,000 observational variables, as is the case with the high dimensional reaction diffusion system, it will become totally unreadable. So there is a widely applied algorithm in this task called SIND autoencoder, which is shown in this figure. Basically, it uses an autoencoder to find a latent space, and then the equation is expressed in terms of the latent variables. And then it predefines the terms that can appear in the equation, which is the thetas here, and such as the constants and the polynomials. And then it learns the coefficients for their linear combinations with sparse regression techniques. So it is very similar to our approach in using this kind of autoencoder structure. So we try to incorporate our symmetry training objective with their equation discovery objective to perform the joint discovery of symmetry and the equations. And the results are amazing. So this is for the reaction diffusion experiment we mentioned previously. And we can see that the discovered equations in 3D latent space with our method contain contains much fewer terms, in fact, only linear terms. But if we only apply SIMD autoencoder, it does work on the 2D case, but not for 3D latent space, where the equations have a lot of second order terms that I have to squeeze them within this data to fit them into this table. And this comparison is about simplicity. And also we observed that the equations learned by our method can have better long-term prediction accuracy. And the bottom figure shows that when we use the discovered equation and an ODE solver to get the future trajectories, our equation on the left leads to accurate predictions within a really long horizon, while the equation from vanilla SIMD autoencoder diverges quickly. And also this is shown in this plot on the right, the observation space prediction error. We show that our method is steady, have a very relatively low MSE error, while the SIMD autoencoder and also the deep models such as neural ODE explodes quickly. So we can conclude that symmetry can simplify the latent space structure and lead to parsimonious equations that are more stable in long-term forecasting. Okay, to wrap up, today we talk about LieGAN and its extension, latent LieGAN, for discovering symmetries of linear and nonlinear group actions. And we also demonstrated the applications of these discovered symmetries in various downstream tasks, such as equivariant neural networks, data augmentation, and equation discovery and long-term forecasting. And hopefully it can inspire you about other more exciting applications with the symmetry discovery algorithm. And for future work, we are considering further extending the search space to local symmetries, which like correspond to the Kate question before. And so this means that the symmetry group may be different across the observation domain, and we need to take as input the axis as the generator input. Yeah, and also we plan to study the connections between the discovered symmetries and other physical properties, such as conservation laws. Because like symmetries are prevalent in the physical world. Ultimately, we want to develop a general framework for automatically discovering symmetries and also other types of governing laws from data, such as the governing equations and conservation laws, so that we can accelerate the overall scientific discovery process. Yeah, and here are the links to our paper and code base. So if you're interested, please, yeah. Yeah, and also for our recent follow-up work, the LieGAN, we have not released the code base, but we expect to release it very soon. So yeah, please pay attention if you're interested. And yeah, thank you for your attention. Kate, do you have a question?
Yeah, I had a question that you sort of, I guess, touched on a bit when you showed the comparison with Cindy, the plot. Yeah, so that plot on the bottom left, with the long-term dynamics, this sort of made me think of the connection with conservation laws, as you were mentioning, right? So symmetry corresponds to conservation law in a dynamical system. So it gives me the impression that what you actually find there might be some kind of conservation law that makes you stay on the same sort of domain or in this limit cycle.
Yeah,
I don't know if you interpret the results that way.
Yeah, it's like the conservation of energy, because if our method preserves this energy while the original SIMD autoencoder does not, this suggests that like maybe their energy is increasing all the time so that it diverges quickly. Indeed, it is very interesting to explore the connection between symmetries and conservation laws. And there are already some works in deep learning that use this kind of neural network to discover the conservation laws from data. I believe there is a work called Noether network where they use tailoring to find a symbolic conservation quantity. And that is also a very interesting topic, and we plan to investigate if we have this latent symmetry, can we somehow derive a conservation law that is the consequence of this symmetry according to Noether's theorem? Yeah.
Yeah, and I would imagine it's easier to start from the symmetry going to a conservation law than the other way around. because you could potentially sort of start from like a Lagrangian or a Hamiltonian with your known symmetry, and then sort of try and derive even analytically a symmetry, a conservation law from that.
Yeah,
so yeah,
it could.
that is very interesting.
Yeah, it definitely could. And like traditionally, physicists are like deriving conservation laws. No, they are deriving symmetries from conservation laws, and not vice versa, not in the opposite way. And we hope that our method can provide like a new perspective on this by first discovering the symmetries, which we believe is easier in this data-driven approach, and then derive the conservation laws. And we hope that it can provide a brand new perspective on this kind of connections. Yeah.
And thank you for the excellent talk, Jianke. I have a question as well here. So
Go ahead.
one thing, so I think one thing in the architecture is you're using kind of a GAN to perform some of the sampling. Did you run into any stability issues in training or like learning the symmetry? Like, does it consistently recover symmetries? Does it occasionally fail and produce pathological output? At least in past GANs I've worked with, sometimes that happens to be the case.
Okay, yeah. So indeed, depending on the random initialization and also the other hyperparameter settings, the GANs occasionally fail to discover the symmetries. And as you know, typically training a GAN is very difficult because it involves different components and different loss terms. So in practice, we might do the same experiments for multiple runs. And then for each run, we will keep an eye on the different loss readings. So if the generator loss and the discriminator loss finally converges to the same value, which is around 0.7 for the random guess on the binary classification, then it indicates that this is indeed the symmetry that we are trying to discover, because the discriminator cannot distinguish between the original and transformed samples. So yeah, in practice, we do this by running multiple times and keep an eye on the generator and discriminator losses. But yeah, there's no guarantee that this optimization using gradient descent techniques can essentially necessarily lead to the discovery of symmetry, although it is theoretically guaranteed that the symmetry can lead to lower loss. But in practical optimization, it might be hard to reach that sweet spot. Yeah, we will have to run multiple times. Yeah.
That makes sense. And maybe as a little bit of a follow-up question, what's like the performance in terms of like, wall clock time? Like, how does the method perform? Say, do you have a chance to do any comparisons with other symmetry discovery methods that people put out there?
Yeah, we did not keep record of all the wall clock running times, but what I can tell is that all these experiments, they can be done in minutes or so. Yeah. Yeah, it also depends on the size of the data set, because we are using the simulated data sets here. And for each data set, the number of trajectories and time steps may vary. So the time may vary from like within minutes or within a minute or several minutes. But generally speaking, it's fast and it does not require a lot of intensive computing. Yeah.
So do you think that so that's actually good to hear, and I think maybe I'll end with the last follow-up part on this. Like, if there's so I know with the reaction diffusion example, you're looking a little bit, I believe, at like real images. Like, do you think the method is robust enough that if you have some, say, messy real-world experimental data, that it could retrieve approximate symmetries like in higher dimensional systems? Like, is that something you think it can generalize to?
Yeah, I think robustness is indeed a good question about this method. And in practice, we often have data that is noisy instead of these perfect simulation data. So I didn't put the results here, but previously for the top tagging experiment here, we showed that if we apply some random noise relative to the original scale by up to 5 or 10%, then the our method can still discover the the same symmetry, which kind of suggests its robustness to noise. But of course, we're also planning to conduct more experiments on the noisy simulated data set, such as we can apply some noise on this image of reaction diffusion, and also in this kind of ordinary differential equation systems. And that will provide more insights on the robustness of this method to noise. Yeah, that's a good question.
Right. Are there any more questions for our speaker from the audience? All right. Do you have a code sample or a demonstration or anything you want to give today?
Oh yeah, I can quickly give a walkthrough about our code. Although I do not actually have any demo, I can explain to you the core components of this method. Yeah. Yeah, so this is the code of our first work, which is LieGAN. And it is relatively simple, the structure of this repo, and the core component lies in this scan.py, where we implement our LieGAN generator. So basically, first there are some initializations, and then the core component is how the generator transform the data. So first we normalize the data to have 3 central dimensions, and then we sample the coefficients from the generator, which is basically the W's mentioned in the talk earlier. And then we use these W's to linearly combine the algebra basis vectors, which is Li's here. And then after that, we have an element in the Lie algebra, and then we use the matrix exponential to get a group elements that actually transform the data. Yeah, so we have different implementations of the distribution defined on the linear combination coefficients, including the Gaussian distribution, uniform distribution, and also uniform integer grid. So for this integer grid example, we're actually dealing with the discrete symmetry case, because the integer grid is a discrete distribution instead of the continuous distributions like Gaussian and uniform, and we can use this distribution to facilitate the discovery of the discrete symmetries, as was mentioned earlier. Yeah, and so this is the core component of our implementation of LieGAN, and then after that, we can. So we provide some scripts to run the experiments in the paper. So basically for the n-body trajectory, which is actually the 2-body trajectory in the main text and 3-body trajectory in the appendix of our paper, we can run these experiments. So the first one is the LieGAN with 2x2 factorization as the parameterization. And also we apply other symmetry discovery methods such as Algorithm, which is adapted to this task because the original algorithm cannot discover unknown groups. We kind of make some modifications to make it also work on this case. And also SymmetryGAN, which is another baseline that can only discover individual group elements rather than the whole group. So we provide some scripts for running the experiments mentioned in the paper, and these should lead to the same result as we report. And then we also have like discrete rotation invariant regression, which is basically this example. So we manually construct this function in this data set and apply the symmetry discovery for a discrete symmetry. And also there are top tagging. So this one may be a little complicated to run because you might need to first download the top tagging data set to the dataset folder. And then we run the similar script as above. And for the baseline comparison and also for the prediction and also the baseline comparison, we need to copy another repository of Lorentz net. So we follow their implementation, except that we are replacing their Lorentz group equivariant neural network with our version of Lie group equivariant graph neural network. So this is Yeah, so first we need to download the converted dataset that adapt to their method, and then we can run these scripts to obtain the results in this slide. So basically, they are the original Lorentz net, which has the best performance with the ground truth symmetry, and the LieGAN, our method, which is only a teeny tiny little bit behind, and also some other methods. They can be run in these scripts. So right now, this is the code base for our first work, and in our recent follow-up work, we plan to release the code in like weeks or within a month. So yeah, you can expect that very soon. Sorry that I do not have a code demo today because because some server issues, so I'm not able to run these codes right now. But if you're interested, please definitely contact me by email, and I'm glad to provide any help if you encounter some problems in using this code for LieGAN. And yeah.
All right. Thank you very much. I think it was very kind of informative talk and code overview there. Are there any more questions from the audience? All right. So maybe then is it back over to you, Keith?
Yeah. Back to you, then I'll hand it back to you for a minute or so, sort of just thank you, Jianke, for the talk. I guess we've seen a lot of work, especially in this webinar, about sort of forcing or encoding symmetries in your models. And I think this is one of our first ones where we talk about actually discovering these symmetries. So if we try and think back, I guess you work a lot with sort of biological applications. Are there sort of any interesting applications or problems that you feel such an approach could help with? Or I guess what's your general take on sort of symmetry discovery and where it might help?
Yeah, I think for biologic data sets, we're actually considering applying our method to EEG data, which is the brain signals from human. So in that case, the signal is very noisy, and it is also very high dimensional, because typically we need to place different electrodes all around people's head, and then for each electrode there is some signal, so the overall signal will be high dimensional. So that we think that maybe by applying the latent LieGAN that is proposed in our follow-up work, we can first reduce this high-dimensional EEG signal into a low-dimensional latent space, and then we discover the symmetry in the latent space. We have not done that yet, but we expect that to be helpful, because as we know, symmetry can improve generalization in the out-of-distribution test data. And for those brain signal data sets, because they are collected from different people, and each person has a distinct pattern of the brain signals. So if we split the train and test set according to different subjects, then for the vanilla deep learning models without symmetry, it may struggle to generalize to new subjects. But we hope that with the symmetry introduced by our method, we can have like better prediction accuracy across the new test subjects. So that is one example that we are considering for the EEG dataset, and that is also an example for that falls in the category of like biological data sets. And I'm really not an expert in biology, but maybe that can remind you of some other settings in biological settings that also require this kind of generalization provided by the symmetry in the model. Yeah.
Maybe to riff on what Jianke was saying there, I'd say, at least in the areas that I tend to work in, it's more, say, molecules, assay data, a little bit sometimes things like microscopy and the like. So there are, some uses of, I think, symmetries, like AlphaFold, I think, is a notable version where that's really had, a market impact. But it's tricky because I think oftentimes, like, the real data is very, very messy. Like, the symmetry might hold only approximately, if at all, and often it's very high dimensional input you're looking at. So I think the challenge that I think there's a lot of potential for these methods, but I think it's also like I think that, one thing I like about, this approach to LieGAN is that it does seem to have a more approximate modeling of the symmetry as opposed to a very rigid structure. So I think that's a bonus. Like, I think in real world applications, like, the rigidity is often like a failure mode as opposed to, like, actually like a success. So it might be interesting to see, like, are there ways to bake in knowledge of symmetries into, like, all these new LLMs, and like there's a lot of work, people doing things like modeling molecules or protein sequences or DNA sequences. Again, this is probably like going beyond what I've seen anyone do in state of the art, but if you can find a way to, like, give approximate symmetry as a primitive operation to, like, a large model, that could be something very interesting. Again, I'm riffing. I don't have any ideas on how this would actually work.
Yeah, that's a very good comment, because like real world data, they contain a lot of noise, which makes any kind of symmetry approximate in the real data sets. So yeah, I think it is also crucial for our method to be able to deal with this kind of approximation of symmetries in the real world data sets. And the plan is that maybe we can like first conduct some empirical experiments on the noisy data sets, and then like try to see what's going on there, and maybe then we can go into the theory and figure out how to make this model more robust to the noises in the real world data.
Maybe as a follow-up question on that, Wayne, what if we don't know if there's a symmetry? Like, is it robust in that case? Like, let's say, again, maybe the toy distribution is there's like two worlds, one no symmetry, the other there's like a defined symmetry. Like, is there a market drop-off? Like, if, say, there's no symmetry, does the model perform a lot worse? If you, like, actually, like, again, this is like, in a synthetic case, this makes no sense. But I can see in practice, you might be like, well, I don't know if there's actually a meaningful symmetry. But does the model still handle that gracefully?
Yeah, so you mean that is there a case where the model with symmetry outperforms the model without symmetry for
no.
really a lot, right?
No, so say you have an experimental data set. You don't know if there's a symmetry, and there is a reasonable chance there is no meaningful symmetry in the data. But can the model gracefully, like, can it gracefully tell you, like, give performance even when there's not a symmetry? Or, is there like a way to easily indicate, no, we don't detect any symmetry in this data?
Oh, so that we are telling by looking at the training generator and discriminator loss, as I mentioned earlier. So typically we claim that we have discovered a symmetry when the generator and discriminator loss becomes close to each other, which indicates that it is indistinguishable. But if the generator loss keeps at a very high level, then we can say that it cannot learn any transformation that preserve the data distribution while preserving the group structure itself, so that we will conclude that there is no symmetry in the system if, like, we run multiple times and yeah, it keeps failing. Yeah, but we do not. This is, yeah. I mean, of course, this is empirical, and maybe we should develop a more like principled guideline for like when to stop and when to indicate there is no symmetry at all, or when we have discovered a symmetry. Yeah.
Right. Thank you for all those comments. Yeah, I'm also very excited to see where this leads to, especially I was really excited by the sort of the function discovery or the model discovery part of this, which I think is where there's a lot of very complicated symmetries to be discovered still. I think in many applications, we sort of know that there's rotation or translation, but sort of new weird symmetries can be found in many, I guess, physics applications and in many equations. So with that, thank you, Jianke, for the great talk, and thank you, Barath, for being session chair. Just to announce next week's talk. So next week we have Justin Barrows, who will be talking about a closed form mathematical framework for modeling turbulent fluids. So thank you all for coming, and thank you for the great talk. I'll hopefully see you next week.
Thank you, Kate. Thank you, Brad.
Yeah.